has been working on multi-agent systems, which I think will be the future. That when these agents, when LLMs become agents, they have to interact with multiple things, and safety is a big thing there. Yeah, looking forward to the talk. Thanks, Aaron.
Thank you. All right. Yeah, so thanks to the organizers for inviting me, and thanks for getting here this early. Yeah, so I guess a couple things before I begin. You'll notice there's a slight change in my title. I didn't actually notice that I had changed the title, but this is actually a better representation of what I'll be talking about today. The emphasis will be on interactions rather than negotiation, although there will be a tiny amount of negotiation discussed. A couple other things. I'm not really going to be, this is the safety guaranteed LLMs workshop. I'm not really going to be talking about guarantees at all, but that seems pretty fair. I think many of the talks haven't discussed guarantees. Slightly more awkwardly, I'm not really going to be discussing much in the way of LLMs either. We're going to talk about things that I think my group is now applying to LLMs. We're going to see a tiny bit of LLMs being applied, but yeah, we were working in this direction. I was hoping to be able to present more in that direction, but we just didn't quite get there. So in the spirit of workshop, this is kind of, think about this as a work in progress, but I really think the nature of the work that we're going to be talking about is certainly relevant to applications in LLMs, and it's definitely where we're going right now. So I think it will still be of interest to you. At least I very much hope that's the case. So as Joshua noted in his talk, and I think Siva also discussed this, I'm sure there were others that discussed this, that LLMs were sort of on the verge of going from LLMs to agents, where these LLMs will be deployed into the world, making decisions on behalf of users. And of course, it doesn't take too much to go from there into a scenario where we have LLMs interacting, or agents, let's say, interacting with other agents. By the way, this isn't actually generated, at least firsthand generated by ChatGPT. I got this off just the internet from the image credits up there, but I'm sure they actually generated it. So this is a secondhand generation. But anyway, the point here is that we imagine that once we have these agents out there into the world, they're going to be interacting with humans, and very specifically, they're going to be interacting with other LLMs and other agents in the world. And in fact, just recently, Google announced, this is 10 days ago. And by the way, if you have questions as I go about, please don't hesitate to ask. Google, about a little less than 10 days ago, released this agents to agents protocol that enables agents to go from to essentially interact with each other, trying to solve a task on a user's behalf, or even go out and interact with other agents from other companies that may be representing other users and interacting between them. So I think we're very much at the point where this is happening, and where these companies are actually going out and working on methods to actually have this interaction. The problem is that, well, there's been actually, I think, a fair amount at this point of thought and effort and thinking about safety from the point of view of LLMs interacting with individual users. And I think this was precipitated a lot from the point of view of ChatGPT. Agent and agent interaction and the safety implications that might emerge are actually something that I think is very much understudied. We're not the only ones to be considering this by any stretch of the imagination. We'll get to that in a bit. But it is something that I think needs more concentration and more study. And so I'd actually encourage anybody who's interested amongst you to go into this area. What I think I'll show you today is a little bit of our efforts in the direction of agent-agent interaction, and we'll see that it's complicated. There's a lot of aspects that are complicated about this. So it can be daunting, but I think we really have no choice but to make progress in this direction, because like we saw with ChatGPT, right, the deployment is leading the sort of considerations of these safety implications. And that's what we're already seeing in this case. So I think the interaction dynamics can actually lead to a lot of safety considerations that aren't actually being addressed right now. So when we talk about that, and we think about the safety considerations of LLM agents and just agents in general, I think we have sort of two ways of thinking about these, or two different kinds of risks that we see before us. And by the way, this is me with ChatGPT. I don't love these, but they'll do. So the two kinds of risks are that I'm viewing right now, at least the ones that we're considering here, are risks that are along the lines of we have different interests being represented, different incentives interacting in negative ways. And I'll be talking a lot about that part of the dynamic. But we also just have agents that interact with other agents where maybe their interests are actually aligned, but they're for whatever reason failing to coordinate in a way that's actually helpful. And in fact, their coordination can lead to very negative outcomes. And in fact, we don't actually have to sort of think about hypothetical scenarios where this can happen. This, in fact, did happen in 2010. Right, we have these agents which were sort of automatic high-speed traders that, because of human market manipulation and introduction of spoofing algorithms, actually led to a cascade of selling off, first in the futures market and then in the stock market, and led to basically an almost $1 trillion loss in the Dow, and just in the course of minutes. Right, because of these high-speed agents. So this is an example of the kind of potential harm that agents out in the real world can do. Even though the individual agents could be considered safe, it's their unforeseen interaction that can lead to this kind of dynamic. So in my group, we're kind of interested in studying these kinds of phenomena and trying to lead to agents that lead to better outcomes when they interact. Like I mentioned, we're far from the only group that's interested in this. In fact, there was just a few months ago released what I would say is a fair representation of the multi-agent game theory community here, released, in fact, a very good report on multi-agent risks from advanced AI. And they essentially broke down the failure modes in these multi-agent systems down into 3 basic blocks. First, miscoordination. This is when agents fail to cooperate despite having the same goals. And the kind of picture that we saw here, I don't think it's fair to say they have the same goals, but it represents things along those lines, I think. The second is conflict. So this is where agents might have different goals, but they could find solutions that are cooperative, and yet they fail to do so. And these are sort of social dilemmas are in this regime here. And finally, we have collusion. This is in cases where, say, for example, where we have a competitive setting like a market where we actually don't want the agents to cooperate, and they might actually find cooperative strategies. So that's kind of a negative side. And actually, I believe Gauthier has actually worked in this third category. But for our purposes today, I'm going to be concentrating on the second category of events. And I didn't mention at the beginning that this is the work I'm going to be talking about today. It was on the slide, but is by primarily led by Juan, who's here. And if you're interested, I'm going to direct complicated questions to him. And Gauthier also was involved in this paper, very integral to the correct development of our math. So thanks to both of them for being here. So I think we're going to go on from this. Now, I've got the obligatory reinforcement learning slide here, which Joshua hates. I knew you were going to react. The reason I'm showing this slide, other than the fact that it's obligatory contractually, is that I'm showing this because this is not, in fact, our scenario, right? Our scenario is that, right? We're going to be considering multi-agent here. For most of this talk, we're going to be considering 2 agents. But we will actually be extending this in a few cases to multi-agents, right? Maybe just one case. But the key thing here, and I'll just go through some of the technical details because it actually, for what's coming, it will actually matter. And I don't know as a group what your experience with RL is. I'm sure some of you are very comfortable with RL, some of you less so. So I'm going to assume a fairly low level understanding of RL. We don't need very sophisticated understanding of RL to follow along. So please bear with me. So we have our 2 agents here, agent 1 and agent 2. They take actions through their policy. Pi 1 for agent 1, it takes action A. Agent 2 follows policy pi 2, and it takes action B. And of course, the policy is conditional on the state and its own parameter values, theta 1 for agent 1, theta 2 for agent 2. And then they make these actions in the environment, and the environment here, through a state transition process, evolves the state, conditioned on the previous state and the action of player 1 and the action of player 2. I'm going to use the terms player and agent interchangeably here. And then they're both rewarded independently. So they get different rewards, and we're going to assume the rewards are in fact distinct, right? So they're not sharing rewards as a general sense here. Now, the key thing about this picture here that I really want to emphasize is that the environment is defined at least in part by the other agent. And this is something that the typical RL setting does not necessarily take into account the way we would like it to. So this is going to be mainly our focus today of the talk, is this dynamic between the agents as they're learning within this environment. Okay, so I'm going to introduce a little bit other notation as we move along. So we've got the discounted return here, which is just the rewards discounted into the future. We're going to also need to consider the probability distribution over trajectories. So this is just given some initial state distribution here. We're basically looking at the trajectory of states and actions that it's determined by the state transition process, as well as the policies of the two agents involved. And then we also have the value. So the value is just essentially just how good is this state S, for the particular agent. So for agent 1, it would be V1, and this is going to be assessment of how good this is, and that's just the expected return or expected discounted return over our trajectory of our probability distribution of trajectories. Okay, and the last thing we're going to need is the action value functions. So these are essentially similar to the value function, only they're a function also of the current actions of the agents at the current time step. So it's essentially how good is Q1 is how good is state to agent 1, given agent 1 takes action A and agent 2 takes action B. And that's the expectation of over the trajectories conditioned on these actions, right? So this is just the action value function here. Okay, so this is essentially the multi-agent scenario that we're going to be looking at, and we are far from the only ones to consider multi-agent RL. In fact, there's an awful lot of work done in this field, but most of it is either in one of two categories, right? In the zero-sum case, that is to say that these agents are in pure competition with one another. AlphaGo is an example of this, where one agent is playing against another agent. One agent either wins. If the one agent wins, the other one loses by definition, right? So that's a zero-sum interaction. The other way that we often see multi-agent RL being considered is in the fully cooperative scenario, where there's a bunch of agents in the environment that are sharing reward, and they're essentially off to try to do the best they can jointly. That's another very popular scenario. We're interested, for the purposes of my talk today, but also what I'm really interested in general, is the case where we're in between those two extremes, where we're really interested in scenarios that are much more about the sort of subtle dynamics between agents that have their own independent interests, but they might be able to sometimes cooperate, and sometimes they're going to be in conflict with one another. So that dynamic is really what we're interested in. And what we're going to find out is that this is, yeah, question?
That both the agents are in the same state?
No, both agents are not in this. Oh, the state. I'm sorry. Yeah, the state here, they do not need to be in the same state. Yeah, I'm not actually reflecting that. The state is essentially the position represents the position jointly of both agents. So there's a question of whether or not that we have full observability or not. Following much of RL, our formalism assumes full observability, but in practice, we often don't explicitly require it. Any other questions at this point? So I mentioned that we're interested in this in-between state, right? Where we call this general sum, because it's neither zero sum nor in the fully cooperative case. And one pretty dramatic context where we're going to consider those are things called social dilemmas. So I'll just read here my definition of social dilemma, which is a type of decision problem where each party's myopic effort to maximize their own benefit leads to a less favorable outcome compared to when all parties cooperate. Right? So this is a social dilemma. And of course, the classic case of a social dilemma is the prisoner's dilemma, which is highlighted here. So we have two agents or two prisoners, and the scheme here is that these two prisoners have been arrested, or that's why they're prisoners, I guess. They're sort of put into two different rooms, and they're given, they're being interviewed, grilled by the police, and they have a choice before them, a binary choice. They can confess, which is to say defect against their co-conspirator and sort of reveal where the loot is hidden or whatever, and in so doing, potentially put all the blame on the other agent, or they can remain silent and cooperate with their co-conspirator. And now we can see the payoffs here that if they both manage to remain silent, we're over Yeah, we're over here, both remain silent, and so they don't reveal any information, any evidence on each other, so they only go to jail for 1 year, right? Now, if they both confess, which is to say they both spill the beans, they both go to jail for 5 years. Now, what happens though, if prisoner B remains silent, but prisoner A confesses, that turns out to be very good for prisoner A. He gets out. We basically put all the blame on prisoner B, and prisoner B is in jail for 20 years, right? And since it's symmetric, the same case for the other one. Now, what makes this a social dilemma is that we're basically in a context where no matter what state you're in, whatever the other player does, you're better off defecting, which is to say you're better off confessing in this case, no matter what the other one does. So this is what we call a dominating strategy. And it's sort of bad news, right, for the players, because there's a better outcome here available to them, but they're just never going to reach it. Because as soon as you can kind of convince yourself to remain silent, it becomes very, very tempting for the other one to confess. So there's really nothing that can be done there, right? So that is essentially the optimal strategy, is just to confess in that case. Where it gets a little bit more interesting is when we repeat this game over and over again, in fact, out to infinity. In this scenario, we actually have a pretty well-known strategy that gives us better long-term returns than we see with just always defecting, which is the famous tit-for-tat strategy. Now, there's a bunch of other strategies. There's a whole nuanced relationship between these different strategies, but this one's a fairly decent strategy. And so this is what it is. On your first turn, you're going to remain silent, which is to say you're going to cooperate. After that, you're just going to copy what the other player did on their last time step. So that's tit-for-tat. Nice thing about tit for tat is that if both players are playing tit for tat, you're incentivized to remain in tit for tat. So it is a Nash equilibrium. Now, there are many Nash equilibria to this particular game, but that's a fairly good one, and it seems to do well empirically in competitions. So this is the kind of strategy we would hope our agents to learn, and we'll see if we're able to do that. Why do I care about social dilemmas? It's not that I particularly care about prisoner's dilemma, but they kind of pop up everywhere. And in fact, where I actually got into this was more in the context, not so much on any of these three, although we are looking at these different options now. Where I got interested in this is because we were playing diplomacy. Actually, we had a project where we were trying to have agents play in diplomacy. And even though the game overall is actually zero sum, if you like, individually, you see there's an awful lot of benefit to cooperating locally. And this kind of dynamic seemed very interesting and actually very hard to recover with RL, which is something we'll get into in a minute. But yeah, so this is where we're mostly getting interested in it. But now, as you start to get into this, as I sort of getting into this field, I start to see these kinds of social dilemmas everywhere. And in fact, a lot of our norms, we talked about, where's Ryan? Yeah, Ryan, yeah, you talked about norms. I think to a certain extent, a lot of these norms come up to avoid these kinds of social dilemmas, right? Like, so there's a social dilemma around cutting in line, right? If you're in a line for something, and there's a norm, a convention around not doing that. I think it reminds me a little bit of what, it's a bit like computer vision, right? Vision is so natural and so easy for us. We don't see the complexity of it and why it took so long for us to actually make advances in computer vision. I actually think that we might see a similar problem with these kinds of norms and social dilemmas. It's such a natural and integral part of how we move about the world. We're kind of blind to its complexities. And I think we're going to be seeing that now with these agents being deployed into the world and their kind of interaction. Yeah, question.
It's kind of an interesting and really surprising point, right? Because like when you think about vision, I mean, yeah, like in the 70s, we had all these like simple 3D ideas, but like thinking about vision today, it's kind of obvious why it's complex. But when you take prisoner's dilemma and you put it in like a game theory context, it does look very, very simple, like simpler than chess or Go, which we've mastered. So interesting, right?
Yeah, but okay, well, two things about that, which I think we'll get into in a sec. But the first point I would say is we're going to embed these games into a rich and complex environment, and they become complex in that setting. So it's not that, and this is actually where I think our work differs from a lot of work in more in a game theory point of view, right? So we're not so much interested in complex dynamics of new game structures, which is really what the emphasis is on game theory. We're interested in what could be relatively simple, well understood games, but embedded within a much more rich context. So that's why we need RL to sort of advance those. The other point is that the interesting thing about this thing about prisoner's dilemma being so simple, the same mechanisms we use, right, so basically RL, to train very sophisticated agents to play chess fail utterly in the context of even simple games like prisoner's dilemma.
Right, that's quite interesting.
Yeah. So yeah, so exactly. So this is basically you know, the punch, well, at least part of our punchline of where we're going to. So we'll get there. Okay, so let's continue on. This is the point we were making, right? So this is why. So we were just talking an awful lot about game theoretic contexts. Why do we care about RL? Why aren't we just using sort of game theory as this? And the reason is because we're interested in these systems behaving in a complex world, right? So we actually want intelligent behavior, which is informed by game theory, but we need more than just game theory because we need to apply these in a rich context. So we're turning to RL because it's the only mechanism I know of that informs how we move to more complex dynamics and agents that behave intelligently in this kind of complex, rich world. The question is can we get them to behave intelligently in the context of these sorts of social dilemmas? And the answer to that is essentially, surprisingly, no. But we're not really here yet with these contexts, right? So we're just a step, we're actually a little bit farther than this, but for our purposes today, we're gonna see this is essentially our complex world here, which is the coin game. So this is just a hair more complicated than Prisoner's Dilemma. But let's look at the game. Okay, so there's a coin. The coin is, for our purposes, belongs to either one color or one agent or the other agent. This is the red color, the red player and the blue player, and this coin is red, so it belongs to the red agent. So if he gets his coin, he gets a point. This is the rules of the game. For a blue coin, if the red player takes it, he also gets a point, but the blue player loses 2 points. Okay, so the pro-social dynamic here is just you collect the coins of your own color, right? Your own coins, leaving the other agent their own coins. And that's a better outcome for both players. Of course, the defecting strategy is just to simply take all the coins you can, right? And that means that the other player will lose every time you take one of their coins and vice versa. So there's a clear defecting strategy here and a clear cooperative strategy here. And at the point I was making earlier, that it turns out that if you give just standard RL these kinds of tasks, and including things as simple as the prisoner's dilemma, they fairly robustly do not find the cooperative strategy. They will sort of beeline for the defect-effect strategy, or the equivalent to defect-effect in the case of the coin game. Yeah.
Standard RL here, is each policy maximizing just the expected reward of that agent,
That's
or right. the sort of joint expected reward?
No, that's an excellent question, and we are assuming that each agent is maximizing their own independent outcome, their own independent return.
And then try to sort of induce cooperation that way? You
could do that. Now you have to talk about how you're going to do that. There's different ways of doing that. We're adopting the point of view. There's particular reasons why we're not pursuing that strategy. And I think the main reason is because we want strategies that induce cooperation in the opponent. Strategies that essentially guide the opponent to cooperation. If you were to do something that you suggest, and this is actually a good point, it's good that we're making this here. Let's imagine that we're just jointly improving strategies, right? And we think about the prisoner's dilemma. What that'll lead you to is a policy that just always cooperates, right? Because you're just jointly assuming that's a perfectly good strategy as long as you're playing somebody that also always cooperates. You put that agent out into the world, what happens is that is a very exploitable agent. And so it's this nuanced point that we're trying to make here, which is we need agents that are cooperative when they can be, but also not going to be exploitable. So that's pretty key. And thanks. I wasn't sure I was going to get to that point, but this is a good time to do that. So right, so we're in this kind of RL scenario, and the reason why I'm saying that RL does not find this, empirically we absolutely find this to be the case, that if you just apply these to problems like the coin game, we're going to see other examples of this, it kind of goes straight towards defect effect or greedy style solutions. And I think I'm going to try to give you some insight as to why this happens, right? So basically it comes down to the fact that as these agents are training, they make no assumptions about the other agent also training, right? They are essentially part of the environment, and the underlying assumption is that the environment is stationary. So that's the scenario we're in, and that is effectively why I would argue why these agents are not actually learning to be cooperative. So let's just put ourselves in the position of this blue player here, right? And it's early in training, so it's trying to figure out how to play effectively this game, and it's playing against this red opponent who's just going to be a fixed random opponent here. And that's the assumption we're making. As an RL agent, our opponent is fixed, right? And early on in training, it's not going to be performing very well, so it's just some fixed random agent. So now if you consider, well, what's the harm with actually taking this blue coin? This guy's just moving around randomly. There is no real harm. There's no repercussion to you. So you are better off taking that coin rather than waiting for the other agent to maybe haphazardly pick it up. So there's a real incentive for these agents to walk right into these kind of defect style strategies. And so, flip it around, and the red player essentially has the same reasoning going around. It's a symmetric game. And so they both sort of cascade into these defect strategies. There's no real, because what it really comes down to is to get out of that kind of strategy and to get into something like tit for tat is a fairly tight coordination strategy in the learning process. So that's what we need. We need strategies that actually enable that kind of tight coordination. Now, this is in the learning process for these agents. This is kind of important to keep in mind, right? So we're not talking about changing agent behaviors in the world right now. We're talking about how do we train policies that enable this kind of cooperative, when possible, kind of play. That's the scenario that we're looking at. Yeah.
Is the rest of the talk still in the Nash setting?
Yes, for the most part, yeah.
So like,
Did you? Okay. Yeah. Sorry, let me back.
That you're describing stationarity, no discounting.
Yeah, we actually do. Well, we actually do have discounting, but we can assume that we're not having discounting for our purposes now.
If you have no discounting in a mesh setting, everyone is like will be capable, spoke here and right, to sustain the best possible outcome. And basically your work is how do we get there?
Yes, exactly. All right, now we're going to do our tiny little interlude into LLMs because we have done some work in this. We're moving this along, but I felt like I wanted to show at least a little bit of our work in this because it's actually kind of, I think, interesting. We'll see. So this is work. There's a lot of interaction and overlap with the other group that's also in this, but this is the group that's essentially pushing this forward. And we're going to do this in the simplest possible kind of negotiation, which is the ultimatum game. So we have Alice and Bob here, our two agents. Alice has a stack of, say, 10 coins or $10, and Alice has a choice. She's going to give Bob a certain number of these coins, and Bob can choose to accept or reject that number of coins. If Bob accepts the coins, they both get whatever the split is that Alice provides. If Bob rejects the coins, they both get 0. Okay, so that's the scenario. And so we give this to, I think we had we're using a Llama 3 7 billion model with LoRa. And I don't have those details here, but they actually matter a lot because the results you get, this is not going to surprise, I think, anyone here. The results you get matter a lot on these kinds of details. What we see, this is, by the way, our setup. I don't imagine anyone can read this, but it's essentially just the rules of the game that we just went through. Plus, we do have this little line here that says, aim to be fair with both the agent and yourself. Now, that matters a lot if you say if we have something like try to be greedy, try to get as many coins as you want, that will have a big impact on the outcome of the play. What we find in our scenario with this model is that it actually takes a little bit of RL training to align to this very specific task. But with a little RL training, the agent does, in fact, learn to be fair and splits the coins pretty much 50-50 both ways. And that's due in part because of the way that these agents have been instruction tuned to be helpful, right? So there's a strong bias in these models actually to be, at least my experience has been, there's a strong bias in these models to be fair. We don't actually have to say this to make that happen. But saying it makes it even stronger to be the case. Yeah.
I would call that an experimental confound, though.
Because we say it?
Because they're like, if you have an agent with a bias towards honesty,
yes.
True, not just this stuff, but other papers, then you're not actually evaluating the game equilibria.
That's right. We're not
going to play incorrectly.
No, but you're exactly right. In fact, what we're going to try to do is undo this.
Okay.
Yeah. So exactly. So this clearly isn't an equilibrium of the game, or at least it's not the equilibrium that we would imagine, right? So the optimal thing the rational thing for Alice to do would be to keep essentially 9 coins. even 10 in some sense, and then to give the minimal amount of coins, I think 1 coin to Bob. And of course, then Bob has to face it. Do they get 1 coin or 0? The rational thing for Bob to do there would be to accept it. And it's interesting to think about this ultimatum game. This is one of these interesting problems that you can spend a lot of time diving into, because it turns out there's actually very different groups, different cultures actually perform this game very differently. There's some tribe in I guess in the Amazon that actually is much more on the rational side of things than what we have with, say, for example, in North American society.
I have a question.
Yeah.
So when you say like algorithm training here, are you adapting the weights? Are you adapting the
Yes,
flow?
we're using LoRa. We're adapting the weights via a LoRa adapter. So we're back propagating and adapting these LoRa adapters. Yeah.
But the prompt is just given stays fixed.
The
prompt.
The rest of the prompt is fixed. Yeah. Everything else is fixed, and we're adapting the parameters. Exactly. So this is basically what we find. So early on, Alice proposes 5 coins here, and you can see it takes a little bit of time, but Bob basically goes to a fully 100% agreement. So there's a small period of time just at the beginning where the returns are actually quite low because Bob has not learned to accept yet. So it actually, with these models, if you use a more sophisticated model like ChatGPT 4.0 or something like that, this basically goes away. It learns to accept right away. So this is very specific to the kind of context we're in. But then Bob's agreement goes to near 100%. Then Alice, and this is interesting, this actually takes quite a bit of engineering effort because Alice is very fixed on being fair early on. We actually needed to, it turned out to be a slightly challenging RL problem to get to actually explore its outcomes because there was very, very high probability of just offering 0.5. So we had to put entropy regularization in and other kinds of things. If we do that, we actually see that it is able to get out of that mode and start exploring around, and it actually gets to this equilibrium where it offers 9. So it actually gets to what you could say is an equilibrium of the problem. It offers 9 coins, and Bob's agreement slightly goes down to around 80%, but that's essentially the setup. Yeah. This isn't an iterated game. Exactly. So what we're exploring now, and this is important to say, right? So this is actually kind of the rational strategy for Alice, right, to explore here. We're not getting into the context yet, where we're actually doing this now. We're looking at the iterated case. The learning problem is just much more complicated. So yeah, we're sort of, and because it's complicated for kind of mundane reasons, right? We actually have to iterate this game. So we have the context becomes very large. So just computationally, it's a bit intensive. But yeah, that's exactly the question. The real good, interesting question for us is, do we see the same exact kind of deterioration of cooperation in the iterated case? Where if you just iterate the ultimatum game and you just take turns between the two, the sort of greedy strategy turns out to be also optimal because it doesn't actually matter how you split, right? If you just agree on both cases, because you can be as greedy on the next turn as well. Where it gets more interesting is if, for example, the case where we were exploring is if Alice, when it's her turn to keep the coins and distribute coins to Bob has a much higher value for those coins than Alice does. So the optimal strategy there is to give away all the coins, and then the same on the other turn. So that would be the interesting case.
I was just thinking of the iterative game where it's always the same offerer and always the same acceptor.
Oh yeah, that would be interesting as well. Actually, you're right, because then Bob has an opportunity to defect. Yeah, that's an interesting setting. We should probably explore that. I think we had explored that. But anyway, we're exploring a lot of different scenarios in that space, but I think that's maybe I'm trying to get to something a little bit simpler, and so maybe that's actually a good one to go back to. Yeah.
Why is Bob noisy and Alice not?
Yeah, it's a good question. I don't know the answer to that. Yeah, I don't know. Yeah.
What's the scientific philosophy of these kinds of experiments? Given that it depends on so many idiosyncratic things, like what's the generalized?
So what we're after here is can RL break the instruction essentially bias of the pre-trained and instruction tuned LLM? That's what we're interested in right now, because what we're interested in, we're not interested in just this game, right? We're interested in more sophisticated things. But if we're going to put agents out into the world and we want to train them in sophisticated contexts where there might be these kinds of social dilemmas, if RL is going to direct our agents towards these kind of defecting non-cooperative strategies, we want to know about that. And there we can start to see if the algorithm that I'm going to be talking about next can actually work in that context. So we're not just interested in this as a one-off. There's a reason why we're asking this particular question. Does that answer your question?
Yeah, I think I was fine.
Okay. Yeah.
Some question why Bob doesn't have a fixed 100% agreement rate, because assuming Alice's policy is fixed at offering only one coin, it seems silly to not just always take the offer.
Sorry, if can you repeat that?
Why is Bob's agreement rate not eventually fixed at 100% if Alice's offer seems to be completely fixed?
Yeah, so I don't know. I don't know the answer. It's possible that what we're doing here is we just have too high an entropy regularization on our policy, so we're really just seeing a bit of noise in the offer. So one thing I'm not saying about this is that when we actually set up the protocol here, Bob isn't just saying yes or no. If it was just that simple, we'd probably have, this actually might get to answer your question, we might actually see 100%. We're making Bob in this context, and there's potentially good reasons, bad reasons to do this. We're making Bob repeat Alice's offer, but symmetric, so that he's getting a certain number and Alice is getting a certain number. So it's not exactly trivial to do that. And so any failure to get the right formatting, actually you can see that here. This is the formatting we're using. So it's just it's symmetric in this case because it's 5 and 5, but it's actually a symmetrical offer. So it corresponds, like let's say Alice took 9 and left Bob 1, then Bob would say, I will take 1 and leave 9 to Alice. And so getting that right is a little bit tricky. So for Bob. So there could be noise in that process, especially since we're adding an entropy regularization on the output. Yeah.
Have you tried to just prompt the model to say, be fair, try to get as much?
Yeah, but we actually are doing that here.
Is there a reason you prefer doing tuning rather than just do that?
Because we want to, what we're interested in getting sophisticated interactions out of our model. And my take on this is rather than just doing prompting, I want to try to see if we can train a model to ultimately do something sophisticated. So what we're after here is, can we get them to be essentially, can we get them to, well, ultimately, this is a first step along a path to seeing if we are in fact going to learn greedy strategies out of this. So this is a greedy strategy, but in this case, it also corresponds to the optimal strategy. So does that answer your question as to why we're going this way? Okay. Yeah.
The order in which the player plays seems to be very important, because if the person that accepts or rejects give it themselves an ultimatum, being like above 5, I would not accept. Then the response of the proposal is to actually give 5.
That's right. Yeah.
So just to know if you think it would be discoverable to actually for the Bob agents to have this kind of ultimatum behavior.
So I think in the repeated game case, the answer is yes. I think so. But it'd have to be in the repeated game case, because in the one iteration version of it isn't rational to do that, right? Because you're penalizing both of you, and as far as you're concerned, this is never happening again. So you get 0 return. You can do better by accepting.
Because you're doing RL, there is a sort of like
yeah, that's not modeled, right? Like that that repetition isn't modeled actually. But it's true that if Alice could be made to believe that Bob will not accept anything other than 5 or above, then Alice would take that into account in our offer. Yeah, you're right about that. Yeah. Okay, anyway, we should move on because I'm realizing we're kind of running low on time. Okay, so what we want to get into now, that was a sort of a side on a game that isn't a social dilemma. It's really important to sort of emphasize that, right? This, like the ultimatum game isn't a social dilemma because the rational behavior there is nothing better than essentially just this kind of greedy play that we talked about where Alice kind of keeps 9 coins, at least for the single iterate version of this game. When we talk about social dilemmas, and I mentioned that RL has this issue of diverting towards this kind of defect style strategy, this greedy play. There is a strategy that overcomes this, and it's basically a class of algorithms known as opponent shaping. And Jacob Forrester was really, I think, a pioneer in this direction with his method Lola. So the basic idea behind and the method I'm going to be describing fits into this category of opponent shaping methods. So the basic idea of these opponent shaping methods is that we're going to assume some dynamic learning dynamics over the other agent. We're going to assume that we're going to have a mechanism that in some ways controls the incentives. Through incentivization, we're going to control the learning dynamics of the other player. So in that way, we're going to essentially shape our opponent as we're training. So this is Lola. This is essentially the first method that described this. The basic idea, the setup for Lola, is that we have a value function. This is a value function for player one that depends on the policy parameters, theta one of itself, of its own model, of its own policy, and the policy parameters of the other agent, right? Because the other agent defines the environment for the original agent. And we're going to imagine that we have we can imagine that the opponent, we're modeling now the opponent's learning, and we're actually going to build that into our own learning of our dynamics. And so we're imagining that in this case, the opponent is going to be a naive RL trainer, and it's going to learn some update of its parameters via a maximization of its own value. And then what Lola does is try to maximize the value, in this case of player one, with respect to its own parameters here, but of this quantity here. So we're taking into account that player two is actually taking a step in its reward maximization or its value maximization. And so we're going to be taking that into account as we're imagining taking our update. Yeah.
I know this isn't exactly the same as like a single agent that joint maximizes utility over both agents,
yeah,
but it feels closer to that than I'm comfortable with. Like there's not that much daylight between them. I mean, because you're giving agent one kind of full visibility into like the policy and mechanisms of agent two and letting it operate it.
Exactly.
And and the utility functions right there, kind of maximizing the sum, right?
Yeah. So okay, so this is a really good point. This is actually what I'll say is it's a very common criticism of Lola. I actually think it's mostly, I think it's like 90% unfair. And the reason why, I'll explain why, because it can also apply to our method as well. It's essentially similar, although I think in our case we make weaker assumptions. The reason is it depends on what you're after, right? We are after methods. So it's this, I think I answered why it's distinct, why this kind of method is distinct from, say, just sharing rewards or joint maximization of some outcome jointly for the two agents, right? That will lead to different policies than what Lola will lead to, right? Specifically, Lola actually leads to tit-for-tat behavior in Prisoner's Dilemma, but the kind of joint estimation will not. It will just lead to pure cooperation. And there's clear, like, that's an exploitable policy, and we don't want that. Okay, so now getting to, I think, the more substantive question, which is, we're making a lot of assumptions about knowledge about the other player. How reasonable is this? Is this a fair way to assess that part of it? Yeah, so I think the way I look at this is, yes, absolutely. If we were modeling, animal behavior or something like this through an RL context, this is an inappropriate assumption. But the way I'm looking at this is much more like how we actually train RL models, right? Or just how we do machine learning. We have a training context, right? We train these models with supervised learning. We do fine tuning. We have a training harness, if you like. And then we're going to deploy this model into the real world. So this is what we do in our training environment. In our training context, we assume all kinds of things about the opponent in our training environment. Then we're going to deploy a policy that's going to be able to cooperate when it can, and it's going to be non-exploitable if another agent is trying to exploit it. So it's that kind of mentality. That's my framing for this, is we are interested in deploying a model. Okay, yeah.
So the other agent is a human.
In this context, no. Are you asking if? Okay.
In fact, the deployment of the agent will be a human.
Yeah.
What can you modify this to work in that setting?
You don't need to modify it at all. You don't need to make any assumptions about
assuming you know the reward function of the human.
Yeah, so just to be clear, like what we publish out of this learning process is a policy, and that policy can interact with any other agents. We're not modeling the other agent at deployment time. Does that make sense? So it will do what it will do, and that could be appropriate for against a human player or not. But you're not making any assumptions about knowledge of the opponent at.
So you know the reward function of the human.
We are not even assuming that. I mean, we're publishing a policy, and it will interact through action space, but it will achieve whatever equilibrium we want. But we're not necessarily. You see what I'm saying?
We'll talk about that.
Yeah, okay.
Try to
Sure.
get better with it. It'd be helpful.
Yeah, sure.
It seems like during training, you're making very weak assumptions about
learning agent, and those assumptions can generalize. Like it's much better than not making any assumptions at all about the learning process of the other.
Yeah, I wouldn't necessarily say they're weak assumptions. They're kind of strong assumptions. But yeah, Fred, that's right.
But they still generalize potentially to interacting with humans.
Yeah, I mean that's right. Like yeah, so I guess that. So I guess what I'm saying is you are imagining, just to answer, Jeffrey, your question maybe more precisely, you're envisioning that to the extent that it does generalize, right, to an agent, to a human that's playing similarly to how the agents have played. Yeah, okay.
So you made two claims, that it's not going to be exploitable and that it's going to cooperate when it can. And are you going to like support those claims?
This is our objective with these methods, okay. Right?
It's not a claim, it's an objective. And
it's an objective.
We believe that.
Well, empirically, we're going to show that it will tend to behave that way. Okay. Like I did say, we don't have guarantees at the beginning. Yeah.
Do you know if this is formally equivalent to what Zico was talking about yesterday? It looks quite similar.
You know, I missed Zico's talk. Actually, Juan maybe could answer that though. Okay.
I'm sorry.
The only talk I missed. Yeah.
Related to this question about not too much distance between just jointly maximizing the expected return, like it's even this framework you're describing where you have this training harness, like in the prisoner's dilemma, even if you have an agent that maximizes the reward of both entities, right? Then if they're against someone who consistently defects, then they'll learn to be non-exploitable, right? And so why not just do that instead of this like slightly weaker assumption of inflow?
Yeah, I can. I'm sorry, I missed. Can you repeat it? Can you rephrase that for me?
Like, what's the advantage of making this slightly weaker assumption?
Slightly weaker than what?
Like you're still assuming that you have access to the how the opponent is updating.
Yeah. So again, like if you're saying weaker than the assumption where we're jointly optimizing, is that the case? Is that what you're describing? So what I guess I'm trying to say is, irrespective of how strong or weak our assumptions are, the goal here is to come up with a policy that gives you something like a tit-for-tat strategy, right? If you were imagine training an agent jointly with another agent, where they're somehow, you're just maximizing their joint outcome, you will very likely come up with a strategy that is something like always cooperate. Both agents will always cooperate. And it has the exact same outcome as tit-for-tat. So you will not be able to distinguish empirically those two strategies. The difference between those two is that one of them is exploitable, one of them is not. We are interested in methods that come up with non-exploitable strategies.
Just try to converge to.
Oh yeah. Okay. Wow. Yeah. Okay. Let's move on. Okay. So we're. Sorry about that. Yeah. So let's move on. So we're going to take a very different point of view on how, well, a somewhat different point of view on how to actually optimize this. So we have our value function here, and we're looking at the expectation over the trajectories of our outcomes as our value function. What we're going to do if we adopt this actor-critic formulation, we can look at the actual actor-critic update gradient with respect to our policies. So we're maximizing our value with respect to our model policies. And this is the advantage function, which is just a regularized or normalized, I should say, rather scaled Q function here. And the issue that comes up is we actually have a term in the policy of our own agent. This is relative to agent one here. We have a term in our own policy, but we have this other term in the other opponent policy. And if we actually follow the gradient, this is going to lead to zero gradient. And this is actually, in our case, this is the term we want to actually have an influence over, right? We want to be able to co-adapt with the opponent's policies in order to lead to, not shared policies, but to policies that actually lead to jointly better outcomes. So we're going to make a very key assumption, different from the assumption that we see in Lola, but our key assumption is that we're actually going to model the policy of the opponent as the exponentiation of its an expectation over its Q function here. So this is a Q function of the opponent. Weakly, we can imagine modeling it if we didn't have access to our actual opponent. But in our case, we're actually going to assume that in training that we have actually. Yes, this is essentially like soft actor critic. It's the same kind of assumption, but we're actually making that assumption about our opponent. So our opponent need not actually follow this kind of parameterization. But if we enforce that kind of parameterization over our opponent, so we're modeling our opponent in this way, what that allows us to do is essentially take the derivative, because there is now an explicit dependency on the parameters of our own policy. We can take derivative with respect to that. And that leads to, if we just follow that, so again, two basic assumptions. The first assumption is essentially the assumption of all RL methods. This is the second assumption that we make, that we explicitly have this explicit parameterization of the opponent policy through its value function. And if we do that, then, and sort of grind the gears of taking the derivative with respect to our parameters, our opponent, well, our theta one parameters here, so the parameters of our agent, then this is what we end up with in this context here. So if we take that gradient, we end up with a term like this, which is essentially basically our opponent shaping term. So very quickly, because we are running wildly out of time, we can have this interesting interpretation of what this term does for us, right? So let's imagine that things are going well for us. We're taking the position of being in agent one here. So let's imagine that things are good. So the past sum over our advantages are positive. So things have been going relatively well for us. What we see is that then what's good for agent two aligns with what agent one's going to, with this term affecting agent one. So if things have been going well for you, you're going to tend to want to do things that are good for agent two. And that's just coming from, this is not because we're adding that directly in. All we're adding in is this dependency on this parameter, right, through our own policy, through this guy here, this parameterization. So we're still only optimizing agent one's value in doing so, but has this effect through that interaction term of improving things for agent two when things are going good for agent one. When things are not going well relatively for agent one, it has the opposite effect. And it tends to punish things that are good for agent two. It makes them less likely and makes things more likely that are bad for agent two. So it's got this kind of interactive term here. Okay, we have some theory, basic. Yeah. People are more empathic. That's a leap that we'll take later. There's time for questions. So I'm going to skip the theory. Just basically, we don't change Nash equilibria, although we potentially change their stability, which is something I think is important to further explore. Prisoner's dilemma. If we apply this method that we call advantage alignment to the prisoner's dilemma, we actually recover tit for tat. This is basically sort of a softer version of tit for tat. We start by cooperating. Then if both players cooperated in the past, we cooperate. If I defected in the past, but the other player cooperated, we cooperate. If the other player defected in the past time step, we defect, which is to say the probability of cooperation goes to 0. Okay, in the coin game, this is the result. So I'm showing you this. You don't have a hope of reading this. This is a bunch of different potential algorithms that we use. I'm showing you this mainly to show that the complexity of evaluating in the multi-agent case, right? Because the environment is defined by the opponent that you're playing. And here we're playing against potentially many different other agents. So how to evaluate how well an agent does, it's very difficult. We basically only have kind of tournament style plays. So the top one, we're going to zoom into that here, right? So this is our method, advantage alignment here against a bunch of other methods. So this is a random agent, always defect, always cooperate. This is in the context of coin game. These are a couple of other methods that are out of Jacob Forster's group. MFOS is a meta learning based method. POLA is in the line of, it's a development in the line of Lola, but much more scalable to higher dimensional problems. I skipped over the problems we see with Lola, but Lola is actually very difficult to expand to higher dimensional problems, more complex domains. And that's exactly what we are trying to do with our advantage alignment. And LOCA is essentially a precursor to advantage alignment. And so what we can see is our method cooperates reasonably well with itself, and does reasonably across the board. It doesn't do great against POLA. You can see POLA takes advantage of Lola, but if in the big matrix, if we look at how POLA does against itself, here, it actually doesn't do very well against itself. It's just a more greedy player. So it tends to take advantage of the other agents. Okay, so now getting really close to the end here, we're just going to look at another place where we've applied this. So Google has put out a suite of interesting games called Melting Pot. One of these is a Common Harvest game where we have a bunch of sprites that are trying to eat the apples. This actually looks a lot like a problem in the context of, what do we call this? Tragedy of the Commons, right? So you can eat the apples, but if you eat all, and that gives you reward, but if you eat all the apples in a bush, the bush disappears and it's never reproduced. If you leave some of the apples, the bush will reproduce more apples. The issue here is you're going to do this in the context of other agents. And the way we actually compare this is, the way we evaluate this, and this is following the evaluation protocol and the challenge they had is, you're going to have 5 of the agents follow your methodology. So in our case, advantage alignment. 2 of the agents are going to follow some greedy heuristic. So you have to kind of contend with these greedy agents. And you can see we're going to compare advantage alignment with PPO. So this is a greedy, well, a pure RL strategy. And this is that pure RL strategy where all of the agents, these 5 agents, are actually sharing reward with one another. So this is like the pure cooperative play. And we can see that as we move on through play, you know, they all lose bushes, but advantage alignment does relatively well compared to both the what we think is a pure greedy play in the pure RL context and with the reward sharing. Because in the reward sharing case, why? Because you have these 2 agents that are greedy, and the agents don't learn to defend against them. Because there's this move where you can actually, you see it here. It's harder to see, but you can actually freeze other agents. You've got this like ray to splash other agents. So yeah. Yeah, these are just the numbers that essentially correspond to that story. Oh, we have a negotiation game set up too. This is not an LLM, but in the interest of time, I think we're going to wrap up there. Okay, so we've had a long discussion about the context of the sort of, let's say, the early parts of the advantage alignment story. We're interested currently in extending to other melting pot games. And as I mentioned before, we're actually also really interested in exploring context of LLMs and negotiations, which is kind of, yeah, where we're actively doing this now. All right, thanks. Questions? I guess we don't have time.
Yeah. This must not be true, but it looked like the derivative of that Boltzmann distribution, because you had Q, it would only account for the change in the next token somehow, and not the full kind of across trajectory modification of the strategy. Are you differentiating Q or just the probability distribution? Yeah, I think Juan wants to answer that.
So Q is actually an expectation over the entire.
Oh, yeah. Yeah, if we go back to the definition of Q that I had, it's
like, you're not like a trained Q, it's like the whole Q.
It's estimated. Yeah, yeah. Okay.
Yeah, you said that yeah, this type of adaptations can actually change the stability of equilibria. Any insights there, empirical?
Yeah, actually, we were discussing that yesterday. So we think that, I mean, this is something we need to evaluate more. Actually, Juan needs to think more about. But we think that it's possible that in the zero-sum case that it results in some of the attracting Nash would be actually repulsive, so they'd be unstable. But we need to explore that more. Yeah, that would be something worth knowing about. Yeah.
Could you give a 30-second overview of the negotiation result?
So we're yeah. I mean what we have here. So this is in the context of like, we're not using LLMs for this. This is just a simple model where the protocol is, this is a rather well-known negotiation game where we have 3 different object types, and the 2 agents, we're given a certain number of each kind of object, and the agents have different values for these different objects. And the idea is, can they divvy up the objects in a way that, you know, maximizes their value? We actually modify this to make it a more clear social dilemma, in the sense that what we do is each agent can propose to take as many of the objects they want. And instead of having to agree, what they do is they just divvy up, like they take the proportion of what they ask for. So if they both ask for 5, then they just divvy, and which is 5 is the maximum, they divvy them both up equally. So so the idea here is that you can kind of easily ask for more and you don't need cooperation to actually make that kind of greedy move. And if you do that, if we just compare our advantage alignment algorithm to, sorry, advantage alignment over here with just PPO over here, what we can see is that, so these are the utilities here, these are the proposals. What you can see really quickly is that PPO is just maxes out, always asks for everything, the maximum amount. Whereas advantage alignment actually learns to coordinate its proposal with its utility after a certain bit of time.
We could stop here, and Aaron is here all day, so thank you, everyone. We'll meet in 20 minutes or so.
Yeah, sure. Thanks for. I realized that.